All right. Hi, everyone. Today we have Zhang from Tianjin University, who will tell us about extensive computations of the atom spectral sequence E2 page at odd primes.
All right, so thanks for the introduction. It's my pleasure to speak here. And let me begin my talk by saying that this is a work in progress joined with Wayne and Lin. So at this seminar, I guess I can assume the audience are already familiar with atom spectral sequence. So its E2 page has the form of X groups over the linear algebra A. And the computation of this E2 page of the sphere is purely algebraic in nature. So in this sense, many people might think, well, this problem is already solved. Well, in the sense that we know how to compute it, and it's purely algebraic. However, the reality is the computational complexity grows rapidly with t. And once you start to try computing these X groups by hand, they will soon become like overcomplicated beyond small ranges. So to compute this E2 page, we need the assistance of computers. And actually, there has been a lot of research in this direction. Well, most of them were concentrated in P equals 2 computations. For example, in 1991, Brunner already computed the additive structure up to T bounded by 116 and multiplicative structure up to T less than or equal to 90. Oh, by the way, so I should mention that there are certainly many other structures on the atom spectral sequence that are interesting and useful and have been studied. But just for the purpose of this talk, we just focus on the additive and the multiplicative structures of the E2 page for this moment. And around 2000, Christian Nassau has already extended the computation to stem like over 200, 210. And Nassau also has unpublished work for odd primes. And some more like recent work in 2022, Brunner and Rogners extended the computation uh, to t less than equal to 200, and that is for both additive and multiplicative structure. And the group Bouvet-Fissor, Dexter Chua, and Hood Chatham, they computed the extended additive computations up to stem 256. And Wayne and Lin computed both additive and multiplicative structures up to t bounded by 2 and 261. And now let's take a closer look at the last two groups and to have a sense of the computational resources taken for such computations. And for the first group, their computations were performed on the Wayne State University High Performance Cluster, which in total has like more than 1,000 cores and over 1,000 GB of memory. And determining the additive structure took several months, and determining the multiplicative structure took 5 days. For Wayne and Lin's program, a Linux program were performed on a single workstation with 64 cores and 256 GB of memory. For computing the additive structure, it took 2 months, and for the multiplicative, it took 3 months. Well, it's worth mentioning that the Lin's computational range for the multiplicative structure is much larger than the previous group. So in this sense, we can say Lin's programs is more efficient and has lower requirements on the machine. So based on the success of Lin's program for P equals 2, we started our collaboration to compute for odd primes. So this is what we have obtained so far. So we have computed the complete algebra structures. That means we have both additive and multiplicative for the following primes in the following ranges. So for prime, we have run the program to for like 3, 5, 7, and 11 to the following ranges. And we can describe the E2 page of the sphere in such ranges as an algebra we can describe the algebra in terms of indecomposable generators and relations. And this table summarizes the number of additive elements, multiplicative indecomposable generators, and algebraic relations. And our program was also performed on the same workstation with 64 cores and over 200 GB of memory. And the time taken for such computations are summarized in the following table. So for each prime, determining the additive structure took around 40 or 50 hours, and determining the multiplicative structure takes much less time. And at this moment, I want to make two remarks. So the first one is, if you compare our program, well, together with Lin's program for p equals 2, compare this with the program from other teams, the main difference is that we have extensively used the other thing called generalized Grosvenor basis theory. So one particular advantage of this generalized Grosvenor basis theory is that it helps us compute this multiplicative structure. So, so one way to say this is, as long as we are able to compute the additive structure of the E2 page up to some range, then there is essentially no real difficulty preventing us from computing the multiplicative structure up to the same range. So you might have noticed that for our program for all primes and for Lin's program for p equals 2, the additive range and the multiplicative range, they always agree. And I would like to also also to point out that the multiplicative structure is very useful. For example, the multiplicative structure together with the generalized Leibniz rule were extensively used in Lin Wang Xu's solution to the last covariant invariant problem. And the second remark I want to make is, well, you might have noticed that for our program for the odd primary computations, the multiplicative structure were determined in a time much shorter than the additive structure. But that's not the case for Lin's previous program for p equals 2. The previous program, the multiplicative structure was determined using a time longer than the additive structure. A main reason for this is that we have optimized the algorithm for computing products. And I will mention that optimized algorithm later in this talk. All right, so now let's talk about the main strategy for such computations. The main strategy, well, is no surprise, a classical one. We try to construct a minimal free resolution of Fp as an A module. So there's nothing new on this page. And the construction is by induction. We first induct on the inner degree T, and then we do induction on, within the same T, we do induction on S. So by induction, we assume we have already obtained a partial resolution which is exact below the degree S comma T. Then for the degree S comma T, we analyze the kernel, we compute the homology, and if the homology is trivial, then that means it's already exact in S comma T, then there's nothing we need to do. If it's not trivial, then for each element in this homology, we find a representative of it, then we introduce a new free generator V to kill this non-trivial homology. And that will make the resolution also exact in the by degree S comma T. So inductively, this
I interrupt. Sorry, this is maybe like a quibble, but like say for each Q, you probably mean for each Q in a basis for capital Q.
Yes, that's true. Yeah. Then we can follow this pattern to finish the construction. And the outcome is, once we have obtained the minimal free resolution, then the X groups are just due to the space spanned by those free generators. It's a property of the minimal free resolution. And just to convey the idea, let's just focus on one particular step of this construction. So there's like one typical question we need to solve during this process. And that is, well, assume we have already obtained an element inside this kernel. How do we know whether this element is inside the image or not? So to better explain this idea, let's draw an analogy in a more familiar setting. So here's an example. So assume we are working with polynomials with rational coefficients. We are given a polynomial f. We are given two other polynomials, g1 and g2. And the question is, we want to decide whether f belongs to the ideal generated by g1 and g2. So here's one straightforward method to solve this problem by using linear algebra. Well, we can assume f has a form f can be read as a some polynomial a times g1 plus some polynomial b times g2. And if we compare the degrees, we find f is homogeneous of degree 3, g1, g2 are homogeneous of degree 2, then a and b must be linear polynomials. And by the way, in our actual application of our program, all of the polynomials we will encounter are homogeneous. So this is a typical situation. All right, so back to this example, we know A and B are linear, so we can assume they have the following form. Because there are only three monomials which have degree 1. Then we can substitute A and B into the equation, solve the system of linear equations. We obtain the answer, we obtain the solution. And then the solution indicates f indeed belongs to this ideal. So this is a perfect solution, and this situation is easy because the degree of f and the degree of g, the difference is just 1. But imagine that we are in a situation where degree of f is like over 100, and the number of these variables x, y, and z, there are over 100 variables, then the situation will be much more difficult. So what happens in practice is that the system of linear equations, the size of the system grows rapidly when the degree increase. So eventually, the system of equation will become like too complicated to solve. So that's one thing to consider with this approach. And to introduce the other approach using global basis, I need to first introduce one definition of like what is a global basis. So assume we are given an ideal of the polynomial ring. Then a global basis G of this ideal is just a finite generating set of it, satisfying some extra conditions. So the extra condition is that the leading terms of G should generate all leading terms of I. So here we can draw an analogy. So polynomial ideals are analogous to linear subspaces. And in this sense, the global basis is analogous to the row echelon form. And that means the global basis not only generates this ideal, but it also satisfies some extra condition, making the global basis, the elements inside the basis, to be well organized with some extra structures. And there's a classical theorem showing that if we start with any finite generating set of an ideal, we have a way to extend that finite generating set into a global basis of this ideal. There's an algorithm for this. So it's not difficult to obtain global basis of an ideal. Another classical result is, assume we have a polynomial f, and we can use global basis to decide whether f belongs to this ideal I. And the theorem is f belongs to this ideal I if and only if f reduces to 0 modulo g. So instead of explaining what this reduced to 0 means in words, I it's better to explain this meaning of this through a concrete example. So now let's go back to the previous example. We are given a polynomial f and g1, g2, and we want to know whether f belongs to this ideal generated by g1 and g2. And before we use Grobner basis, there's some preparation we need to do. We need to fix a monomial ordering. And here, let's say we fix monomial ordering by a lexicographical order. So we assume x is greater than y, y is greater than z. Then we can talk about the leading term of monomials, of polynomials. And now the first thing we need to do is we want to extend this generating set G1, G2 into a Grobner basis of I. And the way to do this is we consider the leading term of G1, the leading term of G2, and we want to generate new leading terms which are not multiple of the leading term of G1, which are also not a multiple of the leading term of G2. And the way to do this is we consider the leading term of G1 and term of G2, we consider their least common multiple. Then we multiply these leading term by appropriate factors. So we multiply this G1 with y, subtract G2 with x. In this way, we can cancel the corresponding leading terms, and there is a chance that new leading terms will appear. And indeed, in this case, we attempt another element in this ideal, and this new leading term is not a multiple of the leading term of G1. It's also not a multiple of the leading term of G2. So a new leading term appeared, and we add this new element G3 to this set, and that forms a Grobner basis. So here I'm skipping a lot of details for the sake of time. But at this moment, let's just take this as a fact that we have a way to verify this is indeed a Grobner basis. And the next thing we need to do is we want to reduce f modulo g. So start with polynomial f. We look at its leading term is x times z squared. And we realize the leading term is the same as the leading term of g3. So we subtract g3 from f to reduce f. And the new leading term is y to the third. And we realize it is a multiple of the leading term of G2. So we add y times G2, and that reduces f to 0. Then by the membership criterion, we know f belongs to the ideal I. And an easier way to see this is we have an explicit expression to show f belongs to I. Sorry, just a second. Yeah, and here the advantage is that we are taking advantage of the multiplicative structure, and usually the Grobner basis is much smaller than the size of an additive basis of an ideal I. So this approach is ideal for high-degree computations. But here is a problem because the classical theorem assumes commutativity. But in our case, we want to work with linear algebra, but linear algebra A is not commutative. For example, if we look at the process for constructing the Grobner basis, we are actually using the fact that y times x is equal to x times y. But that is not true for the linear algebra. However, it's still possible to generalize the Grobner basis theory to A modulos. And the key insight is that the linear algebra A has a main filtration. And working with the main filtration, the associated graded algebra is commutative for p equals 2, and that is graded commutative for all the primes. So in some sense, although the linear algebra A is not commutative, it is also not far from being commutative. So from this utilizing this perspective, we now has extended the classical Grobner basis theory to work with also A modules. So our program and Lin's program our program for alt p and Lin's program for p equals 2 are both using the generalized global basis theory. So the theoretical part are analogous. And in practice, the main differences are each step of our algorithm need to take care of a coefficient and take care of the signs. Sometimes we use plus, sometimes we use minus. There's an extra thing to be careful about. And we also have generalized algorithms for A
Wait, can you
modules.
go back a slide?
Yep, sure.
I want to ask about the lower left corner. I think
Mm-hmm.
that the upper left corner, that's like the classical commutative
Yep,
algebraists, right?
yep, yep,
And
yep,
then and for sure going to the right, that's Waynon's innovation. Are you saying that
yep.
also going down into the lower left corner, is that also like not something that the commutative algebraists had already done?
Yeah. Well, so this vertical map is classical and it's not difficult. So
Okay,
basically,
got
um,
it.
I won't say it's trivial, but it's not difficult.
I got it. I got it
Yep.
now. Thanks.
Mhm. Yeah, and for A modules, we also have generalized algorithm. So the first one is if we start with a structure map in the minimal resolution. So assume the S state of the minimal resolution has n free generators. We know their image. Then we can extend this n image into a global basis of the image module. And moreover, for each of these H1 to HM, we have also chosen a pre-image of these elements. So this is an algorithm that generalizes the classical construction of global basis. Another thing we have is membership testing. It's directly analog to the classical counterpart. We can use global basis to detect whether an element F belongs to the image or not. So using these algorithms, we have an efficient way to construct the minimal resolution. And for the multiplicative structure, so previously I have mentioned that the constructing a minimal resolution is basically equivalent to determining the additive structure, but the multiplicative structure is a different story. So given an element A inside this X group, then well, since the X group is dual to the space spanned by those free generators in the minimal resolution, so I can represent A as a map from the S step of the resolution to the base field Fp. Similarly, for another element B in the X group, I can find a representative for the element B as a map from Fs prime to Fp. So now I have two maps, X from Fs to Fp and Y from Fs prime to Fp. To compute the product Y times X is, and that means we need to take a lifting of the map S as a chain map between the resolutions, and then I take the composite. So in practice, to compute products of these X elements, the main difficulty is that we need an efficient algorithm to find the liftings. So to freeze this problem, this means we are given an element F and we know it is in the image of the structure map. And the problem is to find a pre-image of that. Well, with a global basis, we have an efficient way to do this. So recall that in the previous step, we have already constructed a global basis of the image of the structure maps. And also for each of these elements, we have already chosen a pre-image for hi. Now, assume we are given an element f and we know it's in the image. And then we can reduce f modulo g, and that should reduce to 0. And that means we will have a sequence of reductions, and eventually it will reach 0. Well, this sequence of reductions precisely give us a formula to write f as a combination of hij. And that means it precisely gives us an explicit preimage for this f. So once we have a global basis, we have an efficient way to decide the preimage of this element. And in other words, the global basis provide an efficient algorithm to compute products in the item C2 page. All right, so far I have mentioned the global basis series and how we use that in our computations. For the generalized global basis theory part, our program for alt primes is analogous to the VNet's previous program for p equals 2. And now let's focus on some differences. So the first obvious difference is that for every step here in the alt primary program, we need always to take care of the signs. There's extra thing we need to pay attention to. A second difference. So for alt primes, actually for the item C2 page, we have an extra grading. And this fact can be considered from different perspectives. Well, one way is it's a classical result that the Cartan-Allenberg spectral sequence collect as E2 page with no non-trivial extensions for alt primes. Well, since the Cartan-Allenberg spectral sequence has triple gradings, the item C2 page should also have triple gradings. From a difference perspective, maybe an easier way to see this is the product formula for the standard algebra A is homogeneous with respect to the tau count. So if you count the number of taus on each side of the product formula, it is preserved. So for the item C2 page, we not only have an T grading, the inner degree grading, we also have a tau count grading, count the number of taus. And the benefit of having this extra grading is that it can eliminate some redundant computations. So sometimes during this computation process, we know a priori that some result will not only land in some bad degree, but we also know it will land in some specific a tri-degree. And in that case, we could eliminate some redundant computations.
So I think what you're saying here is that you're using the known Cartan-Allenberg filtrations of things in order to rule out, in order to filter these unnecessary cases.
Basically, yes. So for each step of the accommodations, I'm not only keeping track of the T degree of elements. Meanwhile, I'm also keeping track of this tau count degree of elements. So whenever I work with some element in A, I know it's T degree, S degree, and also its tau count degree. Yes.
I'm saying what I'm saying is I think the tau count is like the same as the Cartan-Allenberg filtration. I guess that's what I'm.
Yeah, that depends on your definition of the Cartan-Allenberg filtration.
Okay, fine. Linear transformation.
Yeah.
Okay,
Yes.
Fine.
Yeah.
Fine.
And another difference is we have improved the multiplication algorithm. So instead of giving the precise explanation of how this works, I realized it might be better if I just give you the intuition of how this happened, why we decide this change. So to determine the multiplication structure of the item C2 page, we did not literally compute the product x times y for each pair of x and y. If we do compute y times x for each pair of x and y inside this range, there will be a lot of redundant computations. Because, let's say, for example, we know a priori that the E2 page multiplication is associative and graded commutative. So there's a lot of computations we don't need to do because that can be deduced from already computed products. So Wayland's program for p equals 2 eliminated a large number of redundant computations. However, there remain some difficult products to compute. Well, in our new program for all the primes, compared to the p equals 2 program, we eliminated a less amount of products to compute. However, we managed to avoid those most difficult ones. And in practice, those most difficult ones will take the majority of time for computations. And as a consequence, although we are computing more products, in terms of the performance, we have obtained a roughly 20 times speed up in practice. Well, the last part is more about the programming, and there's not much math behind it. And the last part is we have, although Wayland's program for p equals 2 already take advantage of parallel executions, and for the alt-primary program, we have redesigned some of the logic for parallel executions to make it even more efficient. And recently, we have plotted our current result on a web page. So now I will stop sharing this slide and start sharing this web page. All right, can you see the web page now? Great. So here you can see this is a plot of the Adam C2 page for prime equal to 3. And here on the top right corner, you can click on this button to switch between primes, prime 3, 5, 7, and 11. Or you can also just right-click on this page. There you can show some like the description of the range here, and also there's like a section for a concise help on how to use this page. Or you can just click on these three dots here to obtain the same information. So with this plot, you can zoom in, zoom out, and click to drag. And you can click on some dot, and then the product is highlighted with green circles. So in the current plot, we only plotted products with A naught and H naught. We have the data for all kinds of products, but we did not plot those information in this web page. And also, we did not display any coefficient. We have those complete data in our database, but those are not displayed here. And yeah, and also there's a convenient method to navigate to a certain point. You can right-click, get help. So you can use the URL parameter. So suppose you are interested in a certain degree. So for example, if you are interested in prime p equals 3, x equal to, so the stem is 140 and the filtration is 20, so you can go to that degree and zoom in by using this URL parameter. You just copy it, paste onto this here, and enter. And that will go to the degree you specify. Your specified degree will be placed in the center of your screen.
Can you show us the Can you show us
Uh,
5, 7, and 11, like zoomed out a
yep,
little bit so I can see the kind of like the global
yep, sure.
structure?
5.
Okay. Can you zoom in around like around the 1260 area? I just want to see how dense it is. Yeah. Around there. Doesn't matter so much. Yeah. Okay. See, it's still
Mhm.
quite sparse.
Yep.
Okay. Great. All right. And then the same thing for 7 and 11. Yeah. Yeah. Okay. All right.
Mhm.
Great. You can skip 11. It's going to be I get it now.
Mhm.
Thanks.
Yeah, then I guess that's all for my talk. I'll stop here.